Hello, welcome to the numerical integration and derivative section of the course. What I've done is created a couple of spreadsheets, actually more than a couple, of spreadsheets for you, and to do most of the examples. So if all you have is OpenOffice or LibreOffice, you absolutely have everything you need to be able to do numerical methods for this. If you've got a programming package, I've also done a couple of programs, and if you've got Maple or anything like Maple, you can use some of the Maple worksheets that I've got. Now, I'm going to try and show you all those, but first I'm just going to start with the spreadsheets. If you pull down the one that says derivative, the first tab is it doing a first derivative approximation. What I do is I just specified a function. Now you cannot give it a function in Excel or any spreadsheet and then just pass it a parameter, unfortunately, unless you're going to do scripting. And if you're going to script, you might as well write in a real program and not be inside a stupid spreadsheet. So what I did was I just took this. I did the example for 3x squared plus 2x plus 5 minus 5. So hopefully you can understand what I'm doing. I specified what h is. I did not ask it, or I did not have it compute h. I just have it as a regular number. Notice that's just my label in A6, and in B6 is where I actually type in the number. I'm going to do this derivative about x equal to 0. If I change this number, everything should automatically recompute for me. And then x minus is my x where I'm evaluating the point minus h. And x plus is that x value plus h. Right, because what we're going to do is a backward approximation, a forward approximation, and a central approximation. And you're going to need x minus I, and x plus I, or x plus h, to be able to do this. All right, so if you just take a look at the formula inside, I know it's very, very long, but in essence, it's just the formula that's in your textbook. Right, to do the backward approximation. Now we know that the first derivative of this thing should be 6x plus 2, and at x equal to 0, it should just be 2. Notice that the backward approximation undershoots, forward approximation overshoots by exactly the same amount, third decimal place, and the central approximation is dead on. If you increase h, you will increase the accuracy of the backward and forward. The central is not going to get any worse. Because it's always dead on. If you decrease h, you will increase the error in both backward and forward. You have to decrease h by a lot, right, to get the central approximation to deviate from the actual. When we do second derivative, again, I used the 3x squared plus 2x minus 5. Right, the h, the x minus, the x plus. And then you need an x minus 2 and an x plus 2 because you have to go 2 steps away. You have to subtract h once and then a second time and add h once and then a second time to do all of these approximations. Now this is, again, backward, forward, and central. And at this value of h, the point, 4 decimal place, I'm getting bang on accuracy. If I change h, though, to 0.1, I still get very, very good accuracy, right? Even though these values have changed, right? So you're going to have to get really gross, right, to get some kind of really weird result, right? Notice I go all the way up to h equal to 2, right, and my second order derivative is still good. Right, so that shouldn't be a problem. You should be able to use both of these and adapt either one of these spreadsheets to do the projects and the homework problems in this section to compute a first derivative or a second derivative if you need to do derivatives. Remember that partial derivatives are exactly the same you just hold one value constant, you hold y constant and do all this for x, or you hold x constant and do all this for y, right? But the computational part of this is exactly the same. All right, so you should be able to adapt these spreadsheets for either one of those. Now for discrete data, I might blow this up a little. In the discrete data spreadsheet, I've got integration and I've got differentiation. I just wanted to show you the data that I've used. It starts at 0, 0, and then it ramps upward to a max and then decreases. It drops off. It's sort of air drag, an air drag problem. Notice that the t-values are not equally spaced. So this is definitely discrete, non-equally spaced data. For both of these, I use the same exact data for both. Notice the derivative for the discrete data is just the I plus first data point plus the I minus 1 data point divided by 2h, where h is the interval between the max and min point here. All right, so what I've got is, notice you cannot do the first data point because you don't have one before it. All right, and you can't do the last data point because you don't have one after it. All right, so you can only do the middle data. All right, and you'll notice here that this formula is much, much easier to do because this is all discrete data. In essence, what I'm doing is I'm taking, that's the I plus first data point. All right, that's the B13 minus the B11, right, which is the I minus first data point, divided by 2 times I, and that's my H. It's I13 minus I11. Right. And that's going to give me my approximate slope. Right. That's really what the derivative is, and when you're doing discrete data, that's what you're trying to find. You're trying to find the slope, or how rapidly the data is changing. Really, you want to know if it's a positive change, negative change, and how large is that change. That's what you're doing when you're doing a very, very quick, dirty analysis of your data. If you're not going to fit a line to it, or if you're not going to try and fit a curve to it, which we do in another module. Right, and then try and take derivatives of that fit if it's a good fit. Right, notice that this continues to increase and rather rapidly up to about 0.5, 0.7 it slows down, 1 it's slowing down even more, it's almost 0 at 1.5, and then it's tipped over. What this is telling you is it's changed someplace between 1.5 and 1.75. This thing changed direction, and now I am in an increasingly negative direction. Right, so the slope of the line is negative. Right, so this function is now, or the data is now decreasing. Right, you can do that if you take a look at the data. Right, someplace around 1.5, and then notice 1.75. It's pretty much negative. Right. So someplace in here, it reached a max, right? And then it's starting to tip over, and this thing gets very, very negative very, very fast. So it's a slow run up and then a very quick tail off. So again, you can use this spreadsheet. You just replace this data with your data set that you're given from the textbook. You should be able to do all your derivatives in here for your discrete data. You don't have to write a program. You can. If you use that same data set, plop it in here, right? What this does is this does integral segments. Right? And again, it's going to take A6 minus A5. Right? It's going to take, that's A6 minus A5. That's your H. Right? That's your, actually your B minus A. Right? Times B6 plus B5. That's the 2 actual data points. And cut that in half, right? So really, B minus A over 2, right? That's half your interval times the 2 values, right? The sum of the 2 values, that should give you a good first approximation to your integral under the curve at that point. What I do is I compute those for each successive term. Again, notice you can't do it for the first one because there's no preceding term. And you can't find the area under a single point. And then, of course, notice when it goes below the x-axis, right, or in this case the t-axis, because this is time, right, You get negative areas, right? So it's going to subtract off from the total. If I want the total area under the entire data set, I just add up this whole last column, right? And I get that thing. So again, you should be able to take your discrete data set and put it right in here to be able to get it to do what you want it to do. Now for integration, it's a little bit more difficult. I did individual data sheets for all of these because you've got a Newton-Cotes open form, and I did the, here I absolutely did the n. This is n equal to 1, that's the n equal to 2 rule, that's the n equal to 3 rule. And then of course I specify an a and a b. You can change a and b and these values will change. It will recompute h, it will recompute your x0, right, for each of these. What I've done is I'm integrating x times sine x, right, for all of this. And if I move this down too far, I'm sorry. I'm going to be doing a midpoint rule, an n equal to 1 rule, an n equal to 2, an n equal to 3, and then I do a comparison. I put all of them together on one piece. You probably want to look at each individual one. Here I did the 3x squared plus 2x minus 5, just as I did on the other sheets. So that you get to compare them. But when I go to the comparison all on one sheet, I've changed the function to x times sine x to give you different values. Notice you get radically different answers. My midpoint rule is telling me 7.27. This is telling me 5. That's 0.9, and that's 1.24. You know, for all of those. And of course, if you go with the polynomial as well, this thing is 44 is the computer answer. Right, for that, for this one, I get a 49.3. That one's a 60, right? And this is actually what it should be. It should be 60. And that one's 60. So the n equal to 2 and n equal to 3 come real close. On this one, you've got all sorts of things happening. And you could do that by hand. You could take x times sine x, integrate it between those two boundaries, 0 to 4, and then go ahead and figure it out, and you could compare both of them. You should also, again, for the assignments, you can absolutely use this spreadsheet. Just change the function. As long as you know what it's doing in the spreadsheet, you can figure it out. It's pretty straightforward on how I have it all set up. All the computation is right there. It should go ahead and just recompute for you. There should be no problems with you doing that. I also do the closed Newton-Cotes form. It could be Coates. I'm not exactly certain how to pronounce it. I do the trapezoidal rule. You'll need understand trapezoidal rule for Romberg. I do Simpson's rule. You probably saw that in calculus somewhere along the line. Right, this is the calculus 3/8 rule. Notice I finally get to 60. You know, trapezoidal rule gives me 92 for that 3x squared plus 2x minus 5 between 0 and 4. All right, so that's not so good. You know, the Simpson's rule gets me to 60. Simpson's 3/8 rule is 60. That n equal to 4 rule gets me 60, and then I do a comparison for all of them. And again, I do x sine x. And notice trapezoidal is terrible. It's telling me it's a negative area. Simpson's rule gets slightly better. It's 2/8. Simpson's 3/8 is 2.25. And then the n equal to 4 rule is 1.826, 183. So again, those you can compare to the open system to see what you're doing. When you do the homework assignments, you should be using a closed version. You should be using an open version. You should be using a Romberg or a Gaussian or something for continuous functions, and you should compare them. You know, which one is better? You should be able to actually do the ones that I assigned. You should be able to do it by hand, get an exact answer, and do an error estimate or an error evaluation to see exactly what the value is, to be able to know this one's better than that one. This one was worse than that one. so you know, so that you could go ahead and use this in the real world, which is the whole point. And the last piece I have is I do a Romberg for you. Basically, the Romberg is based, and I put it right in the spreadsheet. It's based on extending the composite trapezoidal rule. So what I've done is I've taken e to the negative x over 10, and I have set up an a, a b, an n, and an h. Notice the n value changes going across. It's 1, 2, 4. Right? That's the approximate integral is you got to 1, 2, 4, 8, 16, 32, etc. And so what I do is, I need the intervals, right? So these are your intervals next to the n equal to 4. I need those intervals. For n equal 8, I need those 8 intervals. And I compute the answer. I go ahead and do the actual integration. And notice this goes from 0.952 to 0.9518, 9516, and this was 9516. Right here, we're getting a very small change between 4 and 8. But the reason I compute these is this is not Romberg, but this is the composite trapezoidal given different n values. But the whole reason for doing this is the next page in the sheet, which is the Romberg integration. In essence, what I've done is I've shown you how we get this first column of data. Those are all your composite trapezoidals. The second column is you're doing Richardson extrapolation, and you're combining those pairs of integrations to get a more accurate one. Then you compare the comparison. Then you compare the comparison to the comparison, and so on and so on and so on until you extrapolate out to this final answer. Right? And again, this is just e to the minus x over 10. So, and notice that you go all the way out here. You really didn't have to go past this third column, actually right here, right? Because this does not change more than that, does not change more than that. Right? But if you change this value, this thing that you are, just function that you're trying to integrate, it will change. And depending upon how complex this thing is, if it's a cubic, or if it's a sine or cosine multiplied by something, you will definitely need to go out here to those. Like if you put x times sine x and copy that thing all the way down, and then you have this, just watch it recompute, you'll have to go out here to like this column, the I column, before you get decent results for some of these. You just need to know that. But again, you should be able to modify this Romberg sheet to do anything or any of the assignments that are at the end or any of the projects. There's no exam for this chapter, but it is absolutely project driven. I want you to take this thing and apply it to all those problems and make it run. I'm going to do 2 more videos, one on programs and one on Maple, to show you how to get this to work in Maple and some of the built-in functions inside Maple. So I will see you at those.